The following content has been provided by RWTH Aachen University.
Good morning, everybody, and welcome to Designing Interactive Systems 1. Today, we're going to continue our discussion of some psychological concepts that govern much of how we interact with the environment. And I promise you the concepts that you'll learn today will be really useful when you go and buy your next microwave or design your next user interface. There are some of the concepts that I find myself referring back to probably most often when we discuss interaction design issues, or we have a UI where people are somehow struggling with it. So I think these will be very useful in practice. Before that, quick review. We talked about Gestalt Laws. So now you can fire up your brains and see if you remember any of the Gestalt Laws. Yeah. Why don't you start?
The law of proximity.
Okay, proximity, so things being close together, being perceived as a group, right? That's always the message behind Gestalt Laws. Go ahead.
The law of similarity.
Similarity, similar things are perceived as a group, right? We got two. Go ahead.
The law of
Good shape, right? So we tend to reduce shapes to be very specific and very simple, we could say. Remember the experiment we did when we passed the drawings back to the front of the class? Yes? Experience, exactly. So when we do see something, we tend to try to file it as something that we've already seen before. That's 4, I think, yeah?
The law of closure.
Closure, what's that about?
That if you have some lines that could form a shape,
Mm-hmm.
there's missing parts, we tend to mentally close them.
Right, and that what you just described is actually already, you could say, like the next stage of it. First of all, of course, a really closed shape is perceived as a unit, and then if it has tiny gaps, we kind of fill those in. You're right. So that's number 5. Yep.
The law of common fate.
Common fate, right? Common faith would be nice too. It'll be a little more of a religious version, but common fate is right. That's the one where basically. Also kind of religious, isn't it, actually, if we think about it? So it basically says when several things move in the same way or into the same direction, we perceive them as a group, right? That's like the tiger behind the jungle, palm trees, and so on. So do you have another one?
Law of
Continuity, yeah. That's the line being perceived as continuous rather than thinking that two shapes suddenly joined up in a weird way. Anything else? Do we have all of them? Yeah.
common area.
Yeah, right. The one where things that are inside a closed shape or maybe a uniform background are also perceived as a group. Right? These are they're quite similar. Good, excellent. So you will be able to see those everywhere you look, right? Because they're just laws. They do apply to your perception no matter what. Then we had a little bit of a discussion on computer science-y aspects of perception and interaction, right? We did try to compute the information content, or basically get a good estimate of how much information can be passed through a UI component between user and system. Does anybody remember the UI, for example, the content of a user interface component that we talked about? You can pick one that you remember. We're really open about that. All right, folks. I'm going to wait until something moves back there. Is there any chance? You can pick your UI component. Yeah, right.
The toggle button, which had the information content of 1 bit.
Exactly, right. The toggle button, 1 bit, because it has 2 states, right? That's a very obvious one. If you were really pressed for space in an application, you would actually be able to store that information in 1 bit and you'd be done with it, right? Whether it's on or off. Of course, not the drawing of the button. That's not the point, right? It can be as elaborate as you want. It's about like what information is being passed about the current state of the UI or the user's decision that they've made to set it one way or the other. We had a couple others. Yeah, you remember one?
The saltiness is 1.5 bit.
Yeah, saltiness was not a really good way of measuring, of creating, high bitrate input exactly, or output. I should actually say, right? Basically, the user would perceive the saltiness from the system. Yeah.
We also have just plain written text.
Yeah, and so 1 letter of text. Any number of bits?
I think it was like with the logarithm.
Yeah. It was something with the logarithm, right? So basically you look at how many options you have, right? And you basically say like, okay, how many, well, computer science you speak, how many bits would I need to store it? In fact, if you look at it from an information theoretical way, not an engineering way, you can have something like, 0.3 bits, right? It doesn't make sense in a technical way, but it does make sense in an information theoretical way. All right, and then we talked about analog and digital scale. So why would I pick an analog scale? What are the advantages of that? Yeah. Yeah.
I think it was like really, so you could like really quickly estimate ranges, and it's also visible where the limit scales and what, yeah, limits end. And I forgot.
Okay.
And changes or trends are recognized quickly.
Exactly. So we've got, first of all, we do see the range, right, from where to where it can go, typically on that scale. We do see very quickly whether that's moving up or down. And quick estimates are also something that you can really do well in rough estimates. And then, of course, the digital scales are kind of like, have the opposite advantages and disadvantages. Then we talked about the conceptual models of designers and users in a model. So conceptual model of the designer, conceptual model of the user, how are they linked? Can somebody explain that? That was the graphic that we were talking about towards the end of the class. Conceptual model designer, conceptual model that emerges in the user, yeah.
So the designer obviously has his own conceptual model of how his design product is supposed to work and look like. But then when he actually makes a product, we have a system image that obviously then is given to the user essentially, because he gets the end product. And then the user has to make his own conceptual model based on all the information he can get from the system image. And in the best case scenario, it should match the conceptual model of the designer, obviously.
Couldn't have said it better. Exactly, yes. And in fact, the interesting thing there is that the system is not the system, right? The system is the whole thing that you give, of course, the whole system to the user. But what they perceive is what's called the system image. So to say, most closely related to basically the UI of the system, right? Anything I perceive about it, I don't see how it works and its innards and what's happening behind the scenes. But from that system image that I can perceive and reason about, I do make up my conceptual model of how I think it works. And that can be very different from how it actually works, as long as it's a model that's consistent and works, and it's the one that hopefully the designers were intending me to have, then everything's good. All right, and we looked at the Swedish hairdryer, and we discovered a couple of issues here. Maybe one word that we might actually want to add here at some point is visibility, right? That's an important one too. So we noticed that the Swedish hairdryer was struggling with visibility of a couple of key things. What were the things I was not able to see in this model, or not able to see well? Yeah. Yeah, right. How to move to different, temperature settings, and yeah, go ahead, back there. Yeah, you don't even know whether there are multiple settings exactly. So we can't see the available functions. We can't see, as you said, how to get to those functions. And what was the third thing we're having trouble? Yeah. Exactly, the current state, right? What's the current setting actually is. It was all a little bit of like, a discussion point, which it really shouldn't be in a hairdryer. Okay, so today we're going to talk about one aspect that actually was also messed up with the Swedish hairdryer, and that is mappings. Now, what do I mean by mapping? You all know mappings from computer science, from mathematics, right? They map. You take one, set of numbers or a range or a domain, and you map it to a different one. That's typically what a function does, right? And here, it's related. In HCI, mappings refer to two directions. One direction is the direction of going from an input device that you have into the computer. So you work with something physical like this remote here. You move I press the button to the left, let's say, and my slides move back one step, right, for example. The other direction, however, exists as well, right? See, there's something going on in the in the world, and it's displayed through an output device to me, and I get a mapping of that, like a reading on a thermometer, for example. So mappings are relationships between controls, actions, and intended results, and they connect the UI elements that we have to the real world. And this works for input devices like controls here, like the joystick or the light switch. They're both input devices if you want. The light switch, hopefully to a very simple system, the joystick to a much more complex one. And what they do is, in this case, the light switch actually is an input device leading to an effect in the real world, right? Whereas the joystick is an input device that leads to an effect in the virtual world, in the computer. Both are possible, and both will mean that you have essentially an input device. And the other direction also exists, right? So here, for example, when your computer has a certain setting of the sound and it displays that to you, that could be this kind of slider, right? So here I can see the setting of the sound being sort of mapped to a gauge that shows me what the current setting is. Well, this one, funnily enough, also doubles as an input device, actually, so I can go in and change that slider myself, but the software could also change it. So it kind of actually works both ways, right? It links between the virtual world of the computer's internal sound settings and the physical world of me being able to see and interact with that control. Taking a much more simpler example from the analog physical world that has no computers involved at all is this thermometer, right? So if you take that thermometer, what does it do? There is a temperature that is measuring, back there at the bulb, and it's turning that into a display that we can read, right? In this case, you can't really interact with it. You can't change that one and hope that the temperature goes down. That would be nice, but it doesn't work that way. So this is a pure output device, if you want, from a physical world value to an interface element that you actually look at. So it's a mapping. All of these are mappings. Now, so mappings always exist when you have a UI component and something that it affects or represents in the real or virtual world. But good mappings are the ones that we're looking for. And good mappings have one quality that makes them basically all be the same in a certain way, and that is they are natural. So what do I mean by natural? Natural mappings are mappings that have an analogy, where if I do something to the input device, for example, in a certain way, the effect in the real world is so similar that it's really easy for me to remember and understand how that mapping goes. So I don't need to read a manual each time I use that control, or really try to remember it really hard each time, or make lots of mistakes. A good mapping actually is something that is, well, we overuse that term in usability, but it's intuitive, right? So I pick it up and I know how to use it. I don't need to think about it very much. We're going to talk more about these ones on the following slides, so don't worry if you don't know the terms yet. But the advantages of having that is I understand it really well, I can remember it really well, and in the end I have a better ease of use in my system. So to start with the spatial analogies, we're going to take a look at a car shop, right? A workshop where you repair cars. And this is a little in-class exercise I would like to you guys to think about for a second. Spatial mappings, by the way, or spatial analogies, are the most prominent example. Those are the ones that you will see most often when you actually think about good mappings. And the task I want you to think about here for a sec is, let's say you've got this car lift thing, and what your task is to put the control panel in place here, to design the control panel that goes on the side of this this car lift that moves the car up and down. So it doesn't sound like a terribly difficult task, right? And it isn't actually. So how would you lay out those buttons, or maybe they are not even buttons? How would you design that user interface? Yeah, go ahead.
I think ideally you should have those buttons or a lever that controls the movement of the car be aligned with the movement of the car.
Mm-hmm.
It should be on a virtual axis.
Mm-hmm.
Vertical axis.
Mm-hmm.
Go up and down.
Mm-hmm.
Left,
Mm-hmm.
right.
Mm-hmm.
Inside and outside.
Mm-hmm. Exactly. So that's right. So you want you actually mentioned an interesting concept, maybe having a lever that goes up and down, and as I move it up and down, the car moves up and down. That would be super natural, right? Why? Because the physical movement I do on that lever is exactly what the car is doing, right? As I move the lever up slowly, the car moves up slowly. As I move it quickly, the car would move up quickly, all that. Mostly we don't get that though, because levers are expensive and there may be other issues. So we often get buttons, but as you said, up should be up and down should be down, right? So this layout, if you did it this way, the mechanics would hate you, right? Because every morning they would walk in and like, which one was up again? And they would have to read the labels on it, right, to figure it out. It's really hard to remember. If you put them that way, they're going to look at it once and go like, sure, right? So they wouldn't even be able to have to necessarily speak English. They would probably still press the right button simply because they assume the mapping to be natural. See how that's working for you, like in terms of usability? It's actually making your job easier. And as you said, a lever that I could actually push up and down would be even better, because let's be nerdy for a second here. What are we actually controlling with these buttons when we press this button? So I'm pressing this button in, and while that button is on, let's say that's a function, right, over time, the button is on or off, right, 1 or 0. I'm pressing the button for a certain time, and while I'm holding that down, the car's position, if you can also imagine that as a function of over time, actually increases, goes up, right? So how is the the button and the position of the car actually related? Maybe those pens work. Sometimes they do. I can sketch this real quick, but it's an easy enough question anyway. So I've got my button, right? So this is my button, and the button basically over time goes basically it's not pressed, and then it's pressed for a while, and then it's not pressed, right? And the position of the car over time would basically be maybe it's over here, and then as I press the button, it actually goes up, and when I let go, it stays at a certain height, right? So this is the height of the car. Again, this is time, and this is the button being pressed or not pressed. So what's the relationship here? Yeah.
The function of the button is a derivative of the height function.
Exactly. So mathematically, this is a derivative, right? The button is the first derivative of the position of the car. Easy enough, but it means that you're actually basically asking the user to do integration in their head as they press that button. And you all know this feeling because you've all held down the button at some point, and maybe to have an alarm clock go to a certain number, and while you're holding the button down, the numbers are going up, but then you hold it down maybe too long and you overshoot, and then you have to figure out how to get back. It's a hassle, right? So that's not the most natural mapping. The most natural mapping of setting a certain time would literally be to take, a lever and turn it, and as you turn it, it changes the time. That would be more natural. So here, again, the slider is also the most natural mapping. Now it has other issues, right? So if you've got your young Atsubi, the young mechanic lying under the car fixing something, and the old guy comes in and eats his sandwich and leans against that lever and pushes it down, it's a big mess. There's a lot of paperwork involved, right? So from a work safety perspective, this may not be the best layout, right? Maybe the buttons are actually safer because they limit the speed with which this car can move. But from a mapping point of view, this would be the most natural one. Or maybe being able to hold onto that car and like a superhero, just push it up gently. The car notices the force that's being applied. Some servos kick in and move the car up and down. Then I would feel like the Hulk, right? That would be nice too. So as you can also see from this already is usability and natural mappings are a question of good usability. It's only one factor in a design of an interface, right? Other factors like work safety, price, all these kinds of things come in as well. All right. So one rule that you can often use, though, when you're designing an interface is that you want to arrange controls. If you have a freedom to arrange controls in a certain way spatially, then you want to arrange them in a way that maps their real-world counterparts. So if we have this room here, and there was a control to control these rows of lights individually, let's say, then I would want to have 5 light switches or whatever it is here next to each other in that same order, right? I wouldn't want them above each other, although that's typically how they end up in rooms, because then you would have to figure out, okay, which one is which, and I certainly wouldn't want them to be shuffled around randomly, right? That would be just evil. So that's a good example of a spatial analogy that works well. Another one is the car stereo audio fader. If you think about that, Let's assume you have a car where you can fade the audio from front to back speakers, right? That's what the fader typically does. How would you arrange that control? Yeah.
I would maybe, because forward and backwards is really not possible in a car, I would do maybe up for forward and then down for backward.
So you're saying, yeah, forward, backward isn't really possible, and you're right. Mostly that's really tough, right? But I could imagine maybe putting a slider onto the center console that I literally can move forward and backward. That would be perfect, right? That would be exactly the same physical dimension. But if that isn't possible, you actually picked a good alternative, which is moving up for moving it forward and pulling down for moving it backwards. Why that is a good alternative, we'll actually get to in just a second when we talk about more mappings. A warning here, as we talk about like home control and stuff like this, this works well for these simple functional mappings where a control basically directly influences the state of a device. It doesn't work so well for what you often see called activity center controls. Norman has some examples of that, like a theater mode or I want to watch a movie mode, right? That's a completely different kind of mapping where you have a button and you press that button and everything sets itself to watch TV, for example. This is nice from a convenience point of view, but is essentially impossible to do well with natural mappings. And if you mess these these activity center controls up, they can get really hairy to understand, to debug, and not use well. And we have been in rooms. I think it was actually this lecture hall where we were showing a movie. And nobody was moving for a while, and the lights were out. And after a while, this thing just thought it should turn the lights back on, right, by itself, because there was some sensor. So it had a setting for a certain scene, but it wasn't working well. All right, but now on to one of my favorite topics are elevators. Yeah, I think that's kind of sad, I know. But elevators, you'll get to really enjoy elevators. Not because of, you can go up and down, although, that's also fun. But no, because their interfaces are sometimes so messed up. So this is one that I found in Heidelberg. This was the new clinic that was being built there. And I walked into the elevator, and I saw this. So my first question is, how many floors does this building have? Make a guess. Come on. 99 floors. Any other bids? Yeah? 2. Any other ideas? 100. Yeah. It starts with 0. Like, yeah, it's like, a true computer scientist, 0 indexed floors. So yeah, it could be all 3 of those, right? And again, this should not be something we scratch our heads about, should it? Next question. Which way is up? What do you think? Who believes 0, 0 is up? Raise your hand. Who believes 99 is up? Raise your hand. Everybody. Oh boy, you would all be wrong. This is awesome. Thank you. It's one of the best results I've ever been getting on this. So here's what's really going on. This building is built into the ground. And 0, 0 is the ground floor, and 99 is the first floor underground. Yeah. So there's only 2 floors at this moment, right? They were apparently expecting this building to continue on with more floors on the ground later on. And that's the idea. Now, any thoughts?
It's basically arithmetic modulo 100.
Yes, it is modulo 100. So I can see the guy who walked in, having to label the elevator in the morning with his little toolbox, and he opened his toolbox and he's like, oh crap, I forgot the minus sign, right? That sucks. What are we going to do? Well, I got lots of numbers here. Let's see. So I could put 1 there, but then 1 and 0, that's really going to confuse the heck out of everybody. So I don't have a minus 1. I have a 99, and if I add 1 to 99, it's 100, and the 100 kind of drops off because we only have 2 digits. It's modulo 100, so let's do that, right? And this is just me second-guessing what this poor guy was doing, right? But, okay, so we can do better than that, right? We could label them better. But here's something that I want to see. Can you apply what you just learned 15 minutes ago? Or actually now, I should say what you learned at last lecture. That's probably more correct, to this layout. So even if you only had, apples and cucumbers as icons to put on these, no matter what you had, could you do a better job, in this user interface? Yeah, back there. Yes, so you would put the two floors above each other, right? So that's, first of all, you do this because what we just talked about, natural mappings, right? That's why I'm showing this here. So that would be a natural mapping to have these above each other. But actually, and this is kind of like the bonus question here, if you think back to what we talked about last week, there is another effect if you look closely. Yeah, do you have any idea?
Sorry, I was going to talk about the closure. They are apart from each other.
Yes.
So it seems like these vertical buttons are related.
Exactly. So you're right and wrong at the same time. You're absolutely right. This is the secret solution here. If you look at this closely, this is closer together than that, right? So no matter what I put on these labels, your eyes are already grouping this and also this, right? Because of, and that's where you went a little wrong, but I get this all the time. It's the law of proximity, right? Closure means closedness, right? So, but yeah, because it sounds like closed, people mess it up all the time. So you'll make that mistake, hopefully not in the exam, but everybody makes that mistake. So yeah, if you did it that way, you would actually use the Gestalt laws to help you, right? So apparently that poor guy also didn't know about Gestalt laws when he was setting that up. But anyway, so we have ways to apply natural mappings to make things easier. We have ways to apply Gestalt laws to make things easier. And if they can all fall together, then almost, as you can see, labelings become less and less important, actually, right? And that's also one of the messages that you get from Norman's book, right? That labels aren't necessarily a good thing, right? They are signifiers that often are there because we weren't able to do a good job otherwise making the UI self-explanatory. Here's another one from my old kitchen. So here's my old stove, and you know, as you can see, well, hopefully see it's maybe a little washed out because of the lights, but there's you know, there are 4 buttons down here, all in a row, and there's, you know, 4 obviously, you know, 4 hot plates up there. So the buttons are all in one row. Yeah, do you want to play with those lights a little, Marcel? Yeah. Ah, yeah, that's Marcel playing with the lights. There you go. Good. Yeah, I think I like this better. Is that okay for you guys? Yeah? All right. So as you can see, because these are all arranged like this, that's not a natural mapping, right? That's just, you know, you have to guess kind of which button belongs to which of these 4 hot plates there. And because of that, you know, they used icons. So signifiers instead, as you often see on stoves, and they're trying to label them so that I know which plate is which one. And here they are trying to use a sort of mapping because they're showing the 4 plates like this in a vertical, but they expect you to kind of transfer that automatically, that, you know, the one that's at the bottom here is the one that's closer to you here. Using, again, the same rule that you were using earlier when you said you could move the stereo fader sort of up and down rather than back and forth, right? That's the same principle here. Down is closer to you, up is farther away from you. Now here's a little issue. As you actually step up to operating distance to the stove, this is what happens, right? So when you're actually cooking, you don't see any of this, right? So you have to kind of remember it or like step back and kneel down. It's really not nice. So what's wrong with the stove? Well, the mappings are obviously not natural, right? This arrangement, if you think about it, again, from a mathematical point of view, can somebody who paid attention at the stochastics class tell me, or in school really, tell me how many options we would have to create mappings between these buttons and the hot plates? Yeah?
24.
Why?
It's 4 factorial, so...
Exactly, 4 factorial, right? So 4 times 3 times 2. So we've got lots of options here. Now, a lot of these are really, really evil mappings that we wouldn't do, right? So you would probably say, all right, we will probably put the left 2 buttons, you know, and make them map the, to the left 2 hot plates, and the right 2 ones should map, to the right 2 ones. But still, that leaves you with 4 possible arrangements. So that requires labels, which, as we now know, often means bad design. So now it's up to you. What's a better solution? What could you do instead? Yeah, back there. Uh-huh. So where would you put the controls? Still at the front, right? Mm-hmm. You could put them, exactly, so you put them next to the hot plate, right? That was what you were thinking too? Okay, yeah, so next to the hot plate. That's the most natural one, right? Because then your Gestalt law of proximity kicks in, right? You know, the eye automatically groups each control with its hot plate. Really nice. Has some other issues. If you ever tried cleaning anything on the top of a stove, you know, that next to a hot plate, that's kind of tough, and there may be safety issues involved. But that would be a supernatural arrangement. Other ideas, yeah.
You could probably put them at the top, so you could see them, even if we use the groupings of two controls for two.
Okay. So flip them around, make them actually be in front of the hot plates, but visible. Yeah, that would improve, you know, the usability of seeing them while I'm cooking, and then I could kind of still do the 2x2 arrangement. Not ideal, but already better than what we're seeing here. Yeah. Yeah, stove. Yeah. You could replicate the arrangement of those two plates as you do in the icons, right? The icons are doing this already. They're basically saying you can map this, you know, to this. Cool enough. So you could do the same with the actual controls. You could arrange the controls in a square at the front, and you would probably be able to map this to those plates fairly easily, right? Because it is a natural thing to just flip these things by 90 degrees. Yeah. Yes, yeah. So from a point of view, like, did I turn off all the plates, right? You know, quick look at your stove, even, you know, through the kitchen door often is enough to see, okay, everything's good, right? That would get trickier, yeah. So it's not always just a win-win scenario, right? You have to balance these things. And welcome to the, you know, the yucky world of design, because what you will be doing most of the time is actually balance options out. You know, that's designing. It's basically trade-off. You know, dealing with trade-offs and finding the spot where you think you're doing the best job. It's not always obvious. Sometimes there are obvious improvements that are not going to have any adverse effects, but very often there are adverse effects. Whether the interface is more expensive, like putting, you know, the controls next to the hot plates is going to be more expensive mechanically to manufacture, etc. Difficult to clean, has some security issues. So there's all kinds of things that you have to factor in. Yeah.
I just wanted to say, with modern induction heaters, there is like a setup where you have it on the stove itself, and then you have the same mapping 4 and 4.
Yeah.
And since it doesn't heat up,
yeah, it's actually safer. Yeah.
Then it's really easy to map.
Yeah. That's another good point. Oftentimes, you know, technology as it moves on will just make some design problems moot, right? They don't longer exist, and you have a new design space that you can explore that actually gives you new options. Yeah.
But one of these induction stoves, you have a new design problem with the dial not being there. You don't have a dial to set the
Right. So it's you know, it's an endless battle. So here, this is one solution that they mentioned, where he just said, like, let's put the 4 buttons, you know, just in the same arrangement in front as the hot plates are arranged on top. Another one would be to put them next to these plates. And since this will take up a lot of space, right, in front of the at the front of the stove, you could actually even work with this, right? You could arrange them like that, and that would already give people enough of a cue. Just look at, we just use a little bit more height in terms of the space that it requires, but already your eye is probably going to say, that looks like the, you know, perspective distorted view of the actual hot plates I'm seeing, which is like this, right? And that's a very close mapping. So I would say, you know, without much extra expense, you know, you could probably redesign it that way, and it would probably give people an easier way to relate to which one is which. All right, so that's the spatial mapping. Now here's another one that is similar to spatial mappings, but pushing things even further. And these are called perceptual analogies. Perceptual analogies are a way to actually make the UI element, whether it's a control or whether it's an output, an imitation of the device itself. Personally, I like to think of this as the voodoo principle. You get a little doll and you poke it, and the real person goes like, ah. So here's an example, right? Mercedes has these car seat controls, and this is taken from the book. And look at this control. It looks like a tiny little seat, right? So and that's sitting in the door actually, so you can see it. And as you operate that, if you push the backrest forward, for example, the actual backrest moves forward. So you can see how this is really also giving people a very nice conceptual model. There's very little ways in which you can get these wrong because you see the seat and you're like, okay, that's the seat, right? And they are very closely linked, of course, to Gestalt laws, right? You basically see this and you think, oh, that looks like a chair, the seat I'm sitting on, actually. And so it combines the advantages of Gestalt laws with this perceptual analogy effect. So next up, we're going to talk about biological analogies. And for this, I have a little bit of an in-class exercise for you to think about. Let's take some dimensions that we can control. Like I showed temperature here as an example. Let's collect a few more examples for dimensions that we can control in a computing system or in the real world. Physical dimensions, anything that you could imagine you want to control or maybe have a display of. What else could we be controlling in the real world? You can just shout them up and I'll just write them down. Humidity, okay. Humidity, more?
Light level.
Light level, okay. What's that?
Rain.
Rain? Whether it rains or not? Okay. Mm-hmm. Wind, okay. We could have wind. Wind is interesting. I'll put this here. Mm-hmm. Time is a good one. Mm-hmm. Other stuff. It could also be stuff inside the computer, right? That you have sliders or stuff for. That's fine too. Audio? Oh, volume. Volume, I heard. Okay, volume. If you have volume, then what else could you do? Oh, did I trigger somebody's personal assistant here? Sorry. Volume and anything else?
I would have contrast.
Contrast. Contrast, okay, yep. Pitch is a good one. Mm-hmm. Tempo. Tempo is interesting. I'll put it up here. Mm-hmm. Brightness, all right. Okay, enough of those. I'll add one more because you didn't mention it, color. What's this grouping I just did here? All of these, which the Gestalt law of proximity is telling you, right, belong together. They have something in common. And these are a little different. Yeah? Uh-huh, a range. That's getting towards where I'm trying to go. Yeah. A clear zero. Okay, so these have a clear zero. That's interesting too. Yes. Yeah, probably. Yeah. I think that's true as well. Yeah.
The ones on the left can be somehow perceived by a human with our natural capability.
Oh, I can see color.
No, but like the volume, we can tell something is louder or.
Yeah. Okay. So that's we're getting there, right? We're getting there. You're saying I can tell something is louder or less loud. I can tell something is wetter or less wet or more or less bright or more or less. So there's something going on here. Yeah.
Maybe the things on the left are stuff that's like natural to perceive, and on the right are like concepts that we learn, like different colors, different times. So
Okay. So it is. No, I wouldn't go that far because audio pitch is also something that you can perceive, right? But you guys are all close to where it is. Okay. Yeah, so you're saying that the ones on the right don't really have something like an upper limit. That's all, you're all poking at the essence here, you're all right. What's the key deal is here, these are, here everybody will agree on what's more and what's less. These all have a natural direction of more of it or less of it. And this is what we call an additive dimension or an additive unit. Right? So more or less humidity, brightness, light level or brightness, rain, volume, contrast, all of those naturally have a way to say more or less. Everybody will agree on what is more than and what is less with these. Color, is red more than green? Doesn't make sense, right? So they, red is more than green, yeah. Except for Marcel, is red more than green? Yeah, it doesn't make sense. Okay.
Obviously the best color.
Okay. Tempo is also interesting because you might say, well, faster is more, but maybe not. Maybe some people will say like a very fast moving, fast music will be less fundamental or important than a very heavy, slow moving piece or music piece. Time is difficult anyway. Right? There is this notion of, yeah, if I have 10 minutes left, that's more than if I have 5 minutes left until I need to be somewhere. But as soon as you get into the circular notion of time, that it repeats itself on a 12-hour or 24-hour clock, it gets really messy, right? Is 3 a.m. more or less than 10 p.m.? It's really hard to say. So, and with wind also, wind intensity, if that's what you mean, sure. But wind direction adds an aspect to wind that you cannot say whether wind from the east is more or less than wind from the west. And pitch, you might think, well, higher pitch is more, right? But similar to what I said about tempo, some people will perceive a deeper sound as more sonorous and more, having more volume, more substance, and will say that's more, right? Whereas the tinny, high-pitched sound is less. So not quite as obvious here. So what I'm basically trying to say is these are messy if you need to design a UI and think about a natural mapping for these. You got to think a bit. You got to work it out and find a good way to do this. For these, it's super easy, right? Because up and down, more or less, is always clear. So if you have a way to create a control for these, and it's an up and down slider, nobody will ever misunderstand it. And they will all remember it immediately. It's like the position of that car going up and down. It's a natural mapping. So that's what these kinds of biological analogies are about. There's a rising level of more, falling level of less. We had lots of these here for which it works. Taste is another one for which it doesn't work, right? Or location, where I am on a map. There's also no clear idea of less and more for those. And so biological analogy, if you have an additive dimension, the UI should be easy to do, and you should try to follow the idea that you map it to something that moves up and down, because we all perceive that as being more or less like the level of water rising. Now, another natural analogy that is biological is ordering from top to bottom. Right? I'm aware of many different writing systems, but I don't know any writing system that writes from bottom to top. They all tend to go from top to bottom. Correct me if I'm wrong here. But what about left to right? Is that also a biological analogy that we can apply? No, right? Obviously, there's writing systems that go from right to left. I hope this doesn't say anything obscene, by the way. I just... Oh, thank you. Okay, I'm glad. And so there it's not so clear, right? So that's when we move from biological analogies that apply for everybody on the planet to cultural analogies that will only apply for a certain part of people on the planet. This sign here is surprisingly tricky to reason through, right? You know what it means, of course. You've probably taken traffic lessons at some point in your life. You're all here, so you've survived traffic, so apparently you know some signs. But how are we interpreting this? And I got a note from a guy from the US who watched this class online, and he said, like, wow, this is super confusing. He says, like, this sign, I could interpret this in all kinds of different ways. He said, like, it could mean that I need to keep to the right because the red is kind of like, trying to draw attention, meaning like go this way. Or it could also mean, and just indicating that there's traffic on the left. It could also mean keep to the left because, the black arrow winds say like going left is good and red is sort of, dangerous, don't go that way. It could also mean like, don't go forward, and there's going to be traffic coming against you, which is sort of what this thing is actually trying to tell us. Where red, basically is suggesting, don't do that, just as it does pretty much in most countries. And then there's, this is really, and he said the final interpretation of this could also be that this is actually a sign that somehow, one screw got loose and it got turned upside down on the pole because it is so weird that, there's a red arrow on the right. There's a lot of different messages here. So if you don't know this sign, if you haven't learned what it means, it's actually not that easy to interpret. But going back to one thing that you said about the slider, the fader, when you said like, if I can't move it forward and back, I'm going to move it up and down instead, right? So the fading, front or back, is not an additive dimension. It's not a natural mapping because of that. Why is it a natural mapping still to do it that way? Well, because if you think about it, we all walk around with, on the ground with our eyes up like, 1.5 to 2 meters above the ground. So what that means is that our optical perspective, like my perspective right now, is that you guys, sorry to say that, you are beneath the guys back there, right? From my perspective, you are lower in my, I know it hurts, right? Yeah. You are lower in my field of vision than you folks. And that's true, and so anything that is farther away, so farther forward, for example, is actually up in my field of vision compared to down here. Now, this would be different if my head was like, 2 meters beneath the ground, right? Then things would turn up, but that's not the case. So that's what a lot of traffic signs use this, right? So they order things in that same way. If you ever noticed, if you go down the Autobahn next time, take a look at the signs. I mean, I know these days we just look at our, our TomTom or navigation GPS, but there are signs at the side of the road and that sometimes tell you which cities are coming up. Take a look at how these are ordered. It's actually surprising. Anybody remember how they are ordered? Yeah, it's something you don't really consciously pay attention to. Yeah?
Maybe it's the closest, the next city will be on the top and then goes further and further as you...
That's what you would think. It's actually the opposite. It's actually the opposite, right? Yeah, you were saying that too. So the city that's the farthest away is actually at the top. And as you get closer, the closer ones are at the bottom. So that's an interesting kind of like, example of that rule of putting things into this kind of perspective. And a lot of traffic signs make use of this, including this one, right? When you take this and map it to the, basically you tilt it forward 90 degrees, right, to do the mapping, then you see, okay, so right-hand lane is moving forward but has a red sign, and the left-hand lane is coming towards you, is moving, backwards if you want, and has a black arrow. So that's how we make sense of this. All right, and boy, I do notice I do keep, bugging these Swedish designs here, but I don't think this is. I think Swedish designs are awesome. I think there's just more people there that actually pay attention to this stuff, and that's why we have so many examples. Because here's another one. This is a ticket machine from Stockholm that Peter Krantz actually. Documented, and he later won a Swedish World Usability Day design contest talking about this. So the Stockholm ticket machine looks like this. And let's assume you don't know Swedish, okay? I'm going to show you how you need to use this. So the first thing you do is you start in the middle and press a blue button 1 to 3 times to tell the machine if you want a ticket for zone A and B, or A, B, and C. Then you move down and press the second blue button once for a regular ticket or twice for a reduced price ticket. Now it's time to swipe your credit card, which you do on the top left side of the machine. Now you have to actually move back to the center and press the green button once, and then your ticket actually appears to the left out here. You do see the problem, right? This is not ordered in a very natural way. So this needs labels. But even if you label it, it doesn't actually help you very much. When you do add labels to this whole thing, which is the case here on this right-hand side, we've got all this stuff shown in here. You're like, okay, so the labels say, oh, down here is step 1. Okay, so I start with this, and then I do this, and then I have to. That is confusing, right? Very confusing. So if you do a very, very simple redesign of this, you could sort it like that. You could say at the very top, you have a button that says pick the number of zones, right? Choose the zones. Then you could have a button, to select your discount, and then you could have something where you actually pay, and then you have something to do to get the ticket. Trick for Tal up there actually is to change your press for speech, and so you could actually trigger this to maybe have a voice interface if you can't see well, and it also has braille labels next to it and stuff like this. But the most important stuff is here. This goes down the from top to bottom just to have a natural mapping that everybody in the world will find more accessible to use than the one that we saw before. On the other hand, this is an example of a stock exchange display. And as you can see here, this is taken from a picture in China. And as you can see here, the positive values, when the stock is doing well, are actually done in red, whereas when it's not doing so well, they're done in, well, it's kind of green, actually. So things like red for negative aspects is not a universally understood notice. So when we do have a mapping, so good mappings are natural. We understand this now, so they are using these analogies, but not all of them are. No matter whether they're good or not so good, what we do is we learn these mappings, we understand them and remember them by creating a conceptual model, right? This is how it works. And so that's why sometimes a mapping, when you look at it without being in the context of actually using the thing, seems weird. But once you use it, it kind of clicks and you understand why it's going on. So for example, you all know if you're driving a car, there's a lever that you have to use for your indicator lights, your blinker, right, to go left or right. And which way do you move that lever to indicate towards the right? Yeah, so how about you? Yeah. Exactly, to the top, same direction as the steering wheel, right? So first of all, top for right and bottom for left makes no sense at all. But once you've sat in this car and actually moved the steering wheel, and as you do this, you elegantly like flick the indicator light on with that moving of the steering wheel, you're like, oh yeah, nobody's ever going to do that wrong, right? Because it's very clear how that mapping works. There's another example for this, which is on a motorbike. When you look at a motorbike that has indicator lights, you'll find that the indicator lights, if let's say the indicator, oh, this is the example of the lights magically turning back on again right there. When the indicator lights are on a motorbike, let's say on the left handle, then in order to turn right and turn the right indicator light on, you have to push a little switch forward. And that will confuse you no end until you realize, why is that natural? Yeah. Exactly, because you need to push your left hand forward because this is how your steering wheel or your handlebar turns on a motorbike to make a right turn. So that's how you can figure that out. All right, and so finally, I told you I love elevators. Here's another picture from an elevator. I don't know, no comment, right? I don't know what's going on here. You go figure it out. As a result, what we now have actually from reading Norman's book so far is we've got a couple design principles. We know discoverability is important, like being able to see the current state, available states, and actions making those easy to determine, that's an important design principle that we can derive from what we now know about how humans think and interact with their environment. We know that a good conceptual model is important, right? So the system image should represent the state and available states and how to get to these. It should do that well, and it should do it consistently, right? Remember the Windows 95 trash can, right? That broke that idea, where the magician kind of failed to keep his illusion up. And then we have the user, when they do interact with that system image, getting a coherent conceptual model of the system. And finally, good mappings, so natural mappings, can be between actions and results, or controls and their effects, or between the system state and its visualization. And all of these should be natural ones, so that they are easy to remember and help us use technology. And finally, giving feedback about results. So what happens when I do something, like when I do flip the hairdryer to a certain setting, or when I do push that button here on the control, there should be feedback happening consistently, as often as possible, so continuously ideally, so that I know that the system is changing, that I'm now at a new position in my interaction with the system. Now that we've seen these, we're going to add a few more tricks to our tool belt in the form of a couple more concepts that are interesting and that are also covered in Norman's book to some degree. And the next one we're going to talk about is going to be constraints. So constraints are like the evil twin brother of affordances, you could say, because constraints are actually things that limit the way in which you can use something. So you're probably, when you think about affordances, you know that they guide me towards doing the right thing in a way, right? An affordance will tell you, okay, this is how this object is supposed to be used. Whereas a constraint will say, will make it impossible to use something, or really hard or inconvenient to use something in a certain way. And so, like affordances, constraints also provide cues for the proper course of action by limiting the things that you are even considering doing. And this is especially interesting in novel situations when you don't, when a user walks up to an interface like that ticket machine, for example, and you don't have much of a cue yet what to do, then it'll help you if, for example, there is a slot in which you can fit a credit card, but there's no way to fit a bill in there, for example, right? That will help you to avoid mistakes. So the goals of constraints are to avoid errors in use and minimize the information that the user needs to figure out or remember when they come back to the UI, simply because lots of things are just not possible, right? And there are a bunch of different types of these, which I'm going to talk about. But I want to see beforehand whether this is making sense to you. Think about a desktop window system, right? A desktop window system with its windows, icons, menus, pointers, etc. Where are we using constraints in a desktop GUI? You've all seen them in use, yeah?
When an UI element is disabled, when it is grayed out.
Exactly, right? Graying out and something on a menu means I cannot select it, right? So it's physically, I'm physically blocked from actually using it. Not in the sense of my mobility being blocked, not being able to mouse over and click on it, but when I do it, it just doesn't do anything, right? It's locked out of function. So that's a very simple example. And why are we graying out things? Because it may be something like print document when no document is open. And printing a document doesn't make sense because we don't have a document open, so it's grayed out. And this, on the one hand, is nice because it keeps me from doing, from making mistakes and going down wrong paths. But sometimes, I don't know about you, I've sometimes had the case where something is grayed out, and I'm like, why is this grayed out? I should be able to do this right now, right? And then that means I haven't quite, gotten the right conceptual model from the system to understand why this is going on. And then these grayed out items are tricky, right? Because I cannot go in and get an error message and say, oh, you can't print because, but instead it's, I'm kept from even going there. And so sometimes it's hard to figure out how to overcome that constraint and how to get into a state where that action becomes possible. There's ways around that, of course. You could have tooltips hovering over even over grayed out items saying like you can't print right now because you don't have something open, or because you don't have a printer connected, something like that. Okay, so there's a bunch of different constraint types similar to what we just saw in mappings, which were broken down into different types just to give them a little bit of structure. We also can do this with constraints. And I should say right up front, with the mappings and maybe even more so with these constraints, these types are not as sharply defined mathematical buckets that you can throw one constraint into as you might maybe wish. Right? They are going to be depending in part on how you look at the problem. But understanding that these types exist, even if they are sometimes overlapping for certain concrete constraints, helps you to look at them with different lenses, right? Look at them from different angles. So we're going to talk about physical, semantic, logical, and cultural constraints here. Again, physical ones are the easiest to understand, and the first ones we start with. Using a photo of myself that was taken yesterday, I guess. So we're going to physical constraints rely on the physical properties of shape, size of something to constrain your actions. So let's say you've got a bunch of keys, and there's one key on there that has this like traditional shape, what keys looked like 100 years ago, right? And you will know that this key will not fit into a modern security lock, right? Safety lock. It won't work. So that's a constraint that already makes it easier for you to figure out the right key on your keychain. Other examples would be if you, for example, there was a system that was designed by Microsoft at some point, and Norman talks about it in the book, that had a battery that you could put in any way you want, right? When you try to insert a battery into a device, like, I don't know, maybe a digital camera or something, oftentimes it's like, okay, which way does this go in, this was designed so that it wouldn't matter. You could just put it in any way. Or USB-C. Thank you for USB-C finally letting us plug in USB cords any way we want, right? That's like the best thing about it. I don't care about transmission speed. I just care about that I don't have to always try twice before I know how it fits in. Because the classic USB must have been designed by people who were really hating the human race, right? Because the shape of the connector looks perfectly symmetrical, right? If you don't look too closely, if you don't actually actively peek into it, I know you've all done this, right? To see where that stupid plastic lip is, right? If you don't do that, you don't know how it fits in. So there you are, like reaching behind your PC, trying to plug something in, like, it doesn't work, and they turn it around, and it still doesn't work, and you figure out it was another problem because you weren't quite hitting it the right angle. So that's evil, right? So USB-C, on the other hand, really makes it, it looks symmetrical, but it also is symmetrical. So the worst things are things that look symmetrical but aren't, right? That's like what USB is doing. Then I'd rather have something like HDMI, where at least I have an actual clue in the shape when I look at it, reasonably closely, that it only goes in one way, right? That's better than trying to trick people into thinking it would fit both ways. And that was actually a wonderful example. At some point, a friend told me about this car. It was a Renault, and he had a key for this car. And again, the key looked like it would fit both ways. You could actually put it in both ways, but then it would only work in one of the two directions. And that's just mean, right? That's not something you do. So anyway, so physical constraints should, of course, be designed in a way that ideally you can see the constraint visibly ahead of time, right? So you want your car key to either fit both ways and then also work both ways, or really visibly only fit one way when you start out. Here's another example, a picture taken from our lab. At some point, one of our research assistants was running a load test of a Kinect camera in our open project space overnight, and that meant that the lights should not be turned off. So what one of his student assistants did, his Heavies did, was he put this thing with like tape over this, and this is literally not just a sticky note saying don't turn this light off, which is more of a signifier, but it also has a metal bent object here that sticks out at an angle that physically keeps you from switching that, from operating that light switch. So it's a good example of a constraint being put in place. If you really, really wanted to, you could probably still operate that light switch, but there's a lot of things keeping you from doing it accidentally. Next up, we've got semantic constraints. These are a little different, so there's no longer a physical, shape mismatch of some sort, but there's more. We're relying on the knowledge that humans have of the current situation and of the world in general to constrain possible actions, right? Semantics, the meaning of things, right? So you could say semantic constraints are those where doing the thing that the semantic constraint tries to keep you from doing just doesn't make sense, right? That's the idea. So if you're putting together a model plane and you get a pilot, then it will only fit in one way, right? It only makes sense to have him sit in the front cabin and looking forward rather than looking backwards towards like his rear seat. Or here in this case, these puzzle pieces physically fit together, but unless something terrible happens to me, this doesn't make sense, right? Of course, our meaning of our world continues to evolve as technology advances. So what might make sense to everybody today may not make sense to them, 10, 20 years from now. This is not a good example of constraint, but you all know that there's still save icons in software that are labeled with a logo of a little floppy disk icon, right? And like, who on earth has ever used a floppy disk in their life these days, right? So these things do get obsolete. So make sure that you use constraints that work for your user population. Again, these can be culture specific, they can age over time, and so on. Next up, after the semantic ones, we've got logical ones. And these two are really tricky to tease apart sometimes. It's really more two different lenses to look at the problem. But logical constraints rely on logical conclusions, so things I can derive irrespective of the meaning of the situation to just constrain possible actions. So, for example, back to building our model airplane, it makes sense, even if I don't know the first thing about model airplanes, it makes sense that all parts of that kit are supposed to be used, right? That I shouldn't have left, a wheel at the end when I'm done assembling it. Or you could also say that certain logical constraints performing a task in an obvious order, like do first this and this and this, when everybody can just reason about it for a moment, not knowing much about the domain, but reason about it for a moment, say, yeah, that's the logical way of doing it, then that makes sense. So in this example here, one puzzle piece missing is also an indicator that something is not right. Oftentimes, and that's where you see all these concepts are not distinct from each other, right? They often influence themselves and they work with each other. When you do use a natural mapping, it often employs or uses a logical constraint, right? For example, putting two switches next to each other on a wall, one left switch for the left lamp and one right switch for the right lamp, is both a natural mapping, but you could also consider it a sort of a logical constraint that I wouldn't try to use the right switch for the left lamp because it just wouldn't make sense. And so that shows kind of the dual nature of constraint versus, a natural mapping or a good affordance. Here's another one, cultural constraints. So cultural constraints are really things that rely upon generally accepted cultural standards to constrain possible actions. One example of this is that labels on something are designed to be read, so you would expect them not to be upside down. And that could help you figure out which side is up on a closed package, even if you don't know the language, right? Not maybe for a good part of who's in the room today, maybe some of you guys can figure it out, but most of you guys may not know these writing systems, however, right? So if the writing system is unknown to you, then you cannot use this cultural constraint, so it won't work for that cultural group. Another example we're going to continue with this box in a second here, but another example is, red equals stop is a clearly cultural constraint because it's not the same in all cultures. So it only applies to a specific cultural group. And this labeling here does not give us a good clue on whether, where up is, because we may not be able to read it. But if you actually add something to it, and even if you don't know the language, I made up a word, right? So you don't need to know what that means, right? You don't need to know what language it is, but you do recognize the writing system, and so you do recognize that this writing is now not upside down, but the right way up. So that actually, without knowing what this word means, already tells you that you're probably holding the box the right way up. So cultural constraints are, of course, one of the root problems then in universal design when you're trying to design for the entire world at a time in one go. And oftentimes you will have to adjust your interface to different cultural groups to make sure that these things don't clash. So we're going to do a little bit of an exercise now where I would like you to work in groups of 2 and figure out 3 examples for objects where constraints help you use them correctly. Okay? And try to find examples for the different types. I know it's hard, but physical ones are usually the easiest ones to come up with. Maybe you can also find something for a semantic or logical or cultural constraints. And a good area to start off with are kitchen appliances, security devices, vending machines, those kinds of things. So see if you can think about something from your own experience, your own stuff that you have at home, or that your parents may have had at home that you've encountered, or that you've seen at a friend's place, and spend a few minutes of gathering these ideas together with your neighbor and figure out 3 examples, and then we'll share a couple of those. All right, go ahead. So let's hear a couple examples of situations in which you've experienced a constraint. Who would like to start with one? Yeah, go ahead.
Do you have an example for logical?
Yeah?
We come up with
the test the model with a multiple choice, but then there's only one valid answer, so you can only choose one. Once you click another one, that one's going to get
Ah, yeah, right. So that's an interesting one. So it basically, the system keeps you from selecting more than one answer.
even if you don't write that it's only one valid answer, the user will get.
Ah, yeah, okay. Well, I could think about this one in 2 ways. I mean, on the one hand, I could think about it the way that you said as a logical constraint, but I could also imagine this as a physical constraint, right? Because there's no way that I could physically select 2 things. You know what I mean? So one of the things that helps to reason about these constraints, I found, is to see, is there any way I could overcome the constraint physically, right? Could I actually do the other thing? Or is it physically impossible? And if it is physically impossible, then we tend, at least it's a good indicator that you could look at it as a physical constraint. Yeah, but thank you. That's a good one. Moodle. Yeah, let's get into the RWTH online systems. There's plenty of stuff with usability. Yes.
When we use vending machine and the drink is sold out, the button turns red. And it can be physical.
Yeah. So the box, the button turns red, saying that this drink is out, right? Okay. You can still press it. Hopefully, it won't charge you for delivering an empty system. If it did that, then it would be purely, I would say, more something like maybe a cultural constraint, because in this cultural area, red means, something bad. And so then the design is trying to use that cultural constraint to indicate, don't push this button. But if you do push it, then you would enter the error situation, basically, of trying to buy a drink that isn't there. But if you say, like, the button physically, it doesn't, the shopping doesn't go through when the thing isn't there, your card doesn't get charged or your money doesn't get taken, then you could also look at it as a physical constraint. Yeah. As long as it's avoiding an error situation, that's good. Yeah, Leonard.
So fire emergency button buildings
Mm-hmm.
physically constrained to not be pushed by accident or something.
Right. There's a glass in front of it that you need to smash first to push them. Yeah, right. Similar to sort of that hook over or light switch at the lab. Yeah. Uh-huh.
A logical constraint would be on a knife that you always hold it the way it cuts.
Uh-huh.
There's no logical reason to hold the.
Yeah, not a healthy version anyway. Yeah. Uh-huh. Okay. Yeah, right. That's similar to like picking up scissors, right? Which we already talked about last time when we said like conceptual model emerges as we use tools. And with these kinds of things, there is only one way to reasonably hold them. Yes, absolutely. You could also look at these as, they could also be looked at from a semantic point of view. If you think like a reason through like what's the meaning of this tool to cut things, and there's a handle and there's a pointy edge. So probably this is the meaningful way to use it. But like I said, these things are somewhat on a blurry line. Any other examples? Yeah, back there. Mm-hmm.
I don't know if this is a stupid example or not, but if you want to cook a deep frozen pizza in the oven, and the logical constraint I thought about is, or we thought about is, if you put it inside the oven and don't turn it on, then the pizza won't cook. So this is not. So is this a logical constraint? Because you can put it in there. There's nothing physically stopping you from it. But the constraint there is logical because it just doesn't make sense to put a pizza in the oven and expect it to cook when.
Yeah. So first of all, kudos for pulling something right out of the very experience of your everyday lives of deep frozen pizza. I love that. But I would say if you actually hold on to that example, like you put the pizza in the oven and then you forget to turn it on, you're saying, right? I wouldn't describe that with constraints so much, but it is actually a wonderful example for one of these slips that we will talk about soon, which are user errors that just happen because of a mild oversight, and which some systems encourage and other systems don't. So we will reason about these, and what you're describing is actually probably a good example for the, what do we call this, premature conclusion, I think?
But I think it also works on one of the next slides, which will be 7 stages of action.
Yeah, okay. So we can certainly place it in there, and then we'll see maybe what's going on there. So we'll hold on to that deep frozen pizza for now. Okay, gonna move on to forcing functions. When we said that physical constraints are the ones that are particularly easy to realize and to recognize, forcing functions are an extreme example of that. They often help to avoid errors, and they are a standard design tool in industrial design and product design and safety design, actually. So safety engineering knows these things. When you take this door, for example, is being installed at a place where you are, let's say there's a fire and you're running down the stairs to get to the exit, but this staircase, this part of the stairs would actually lead you into the basement where you can't get out. Right? So you're running down the stairs, and you just take another flight of stairs because you're running down the stairs and you're panicking and there's flames everywhere. So this thing keeps you from making that mistake, this potentially fatal mistake. So you actually have to open this gate pretty awkwardly to get down there. Now, of course, what we see here is that this places a burden on everyday use. Right? Every time I want to get down into the basement, I have to open this stupid gate, and it's probably going to be annoying for you many times until it saves lives in a fire. So forcing functions really, I think, illustrate really well that there's a price to be paid for these kinds of constraints, right? And it's another example of this design balancing that you will be doing when you design interfaces all the time, that you have to figure out how much am I making things worse on that end, but how much am I gaining things on this other end. Seatbelts are another example of this. You know that modern cars often will annoy the heck out of you if you don't fasten your seatbelt, right? So the car I have is it will beep at you occasionally. Then if you go for a minute, then it will beep more often, and it gets louder, and you're like, man. And normally that's great, right? Because you want to fasten your seatbelts. But I know that, for example, like taxis are often Mercedes cars, right? So, and taxi drivers are sometimes asked to like take a package or something on like the passenger seat, right? And if it's a heavy package, the system will think that somebody's sitting there. So it'll ask you to close the seatbelt, right? Which you can't really do in a reasonable way around a package, right? So here you are as a taxi driver. You get the deal of your life, of your dreams. You have to drive this parcel from Hamburg to Munich, right? You're making a ton of money, but for all these 8 hours of driving, this thing is going bing, 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 and you're going to go nuts. So one of the things that really sells well among taxi drivers, I've been told, are these tiny replacement seatbelt locks that you can actually just have there and then jam it into that seatbelt receptacle so that this thing shuts off. So it shows again, there's a lot of good reasoning that goes into making a forcing function like that, right? Because it's safety engineering, but it can also lead to significant usability issues. We do tend to differentiate between certain kinds of forcing functions, and again, not a crystal clear distinction that you can mathematically determine one way or the other, but more different lenses to look at it. One way to look at forcing functions is locking out a certain action, right? So lockouts are preventing certain actions, like this stairway to the basement. It's keeping you from doing that, right? Another way to look at them is a lock-in that keeps you from prematurely stopping an action. For example, on a computer, you often these days have a soft power off button. When you hit that power off button, it'll actually pop up a dialog saying like, okay, are you sure you want to shut this thing off? And it's going to give you some options to save things, etc. So that's keeping you in the on state to make sure that everything gets saved and that you shut down the computer safely to avoid any data loss. And the third kind of forcing function after lockouts and lock-ins is the interlock. So the interlock actually is more there to enforce a certain sequence of things happening. For example, when you take a microwave and you open the door, it turns off, right? So there is an interlock that says, I'm always gonna first turn off the microwave generator before the door opens, and that's mechanically, electrically built into the system. Another example that I really thought was ingenious. I'm gonna draw that. So there was a shelf. I'm not sure where this was. It might have been UK airports or something. But anyway, so you went into a restroom, public restroom there, and we're going to look into the restroom from the top, okay? So here's your restroom, and let's say here we have the door that opens to that restroom, and it opens to the inside, right? So I got to think through this real quick here. Yeah, so it opens like this, right? Okay, so that's the door opening, and when you got in and you closed the door, and closed again, then there was a shelf that you could put down to put your stuff on, right? Which is great when you have lots of, you maybe got your baggage with you. So that shelf was flipped up against this side of the room, but it would flip down for you to put stuff on. So you put your things there. The thing is, in order to get out of that bathroom, right, out of that restroom, you actually had to flip that shelf back up. Guess what? Nobody ever left things behind in that restroom, right? Because they were forced to take everything off the shelf before it would flip up, before you could open the door. It's a wonderful example of safety engineering, or in this case, more like a convenience thing that keeps people from forgetting their stuff at the airport. Right. Let's go over the last big concept we're going to be covering today. And this is a really nice model that helps you reason about how people break down something they want to achieve, they want to do. Oh, I'm getting actually wind here. I'm going to close that window maybe. How people break down a task that they want to complete into a sequence of actions. How do they get from a somewhat hazy general goal or something they're unhappy with currently, what they want to change, to actually rolling out a series of actions to get to that. And this is called the 7 stages of action model. So it's a basic model that says how people do things, okay? And here's a zoomed out view of that model. that doesn't have the 7 stages in there yet, but it shows you the overall structure of that model. It's very simple. We will start looking at the goal. You don't always start the cycle at the goal, but for now, for understanding it, it makes most sense to start there. So you've got a goal that you want to achieve. So then you do something, you execute something, you change something in your environment, in the world around you, right? You have some kind of physical interaction with your environment. And then you evaluate whether what you did actually led to the result you were looking for. And then hopefully you're done, right? So this is the basic model, and we're going to look at this in more detail. But why are we doing this? We're doing this because at each of the steps in this model, things can go wrong. And we're going to look at the various transitions that happen as we go, as users go, as people go through this cycle, and understand what can we do in interface design, in interaction design, to actually avoid mistakes at that level of this psychological cycle, if you want. So each action has these 2 parts: the execution and the evaluation part. And the 7 stages of action model is basically giving us a fundamental view on this whole process. So let's now zoom in on the left-hand side, the execution part. Okay. So the execution part starts with a goal, as we said. We form a goal, and this could be as simple as it's too dark in this room, right? I'm having trouble reading something. And then the plan that we formulate then is that we say, oh, I guess I gotta turn on the light, and turn on the light switch back there at the door. Then next up would be specifying a concrete action sequence. And I like to think of the action sequence as something you could tell a robot to do, like go forward, stretch out your arm, push your finger on the light switch. And then you perform the action sequence, and that's when it actually happens, and you change the environment around you, right? You do flip that light switch. So the goal formulation, if we look at that in a little bit more detail, means that they are very, very vague often and problem-oriented. Like I said, I need more light, for example, right? They first need to be turned into something that actually is a plan, right? So the goal is somewhat vague and doesn't yet tell me how to achieve it. It just is something that I want to have to be different than it is now. Whereas the plan then is actually telling me concretely what I'm planning to do to get to that goal. So that's then the goal-oriented plan, like operating the light switch. And then you specify these out into action sequences, like I'm sitting down, turning around, stretching out, pushing that light switch. And note that, of course, at each of these levels, even if I have a goal of, I need more light, I could come up with a different plan. My plan could be just, instead of saying operate the light switch, I could say, Marcel, would you mind turning on that light for me? Right? That's no, that's okay. So that's a different plan that would also be able to hopefully, satisfy that goal. And even if I have a plan, then maybe there are different ways to execute the action sequence to get there. Right? Maybe I can, get up and push a button, or maybe I can grab a stick and push it with the stick instead. Right? So there's different ways of doing that. Now let's look at the right-hand side of the 7 stages of action model. This is where you move from what happened to the world, to the environment around you, which you need to first perceive, right? You need to see what was the effect I actually had on the environment. And then you need to interpret what you did there and sort of understand what kind of effect it was. And then you need to figure out whether that actually completes your goal, whether your goal has now been fulfilled or not. So there is perception, interpretation, and comparison. Those are the 3 steps that you go through until you end up back at your goal. So as a whole, this is what the model looks like, right? Execution on the left-hand side, planning, specifying, and performing it, the action sequence, and then perceiving that change, interpreting it, and comparing it to the goal. Now, if you think about perceive, interpret, compare in the example of our light switch, you could say, once I've flick that light switch, I first need to perceive the new brightness in the room, right? Then I need to interpret it as, you know, can I now actually read the book that I was trying to read? And once I figured that out, then I compare, is that what I wanted to actually reach? And have I reached my goal of having enough light to read that book? So in some examples, depending on the task, sometimes perceiving and interpreting are actually going to be quite different. We're going to see some examples of that. Now, of course, in reality, these steps are kind of hard to distinguish, meaning that, again, this is a model, right? But humans don't, you know, go through and like, I have a goal and now I make a plan, right? That's not how we work. This all happens subconsciously. It happens in parallel. We, you know, we often have hierarchies of sub-goals. So, for example, to, you know, maybe to turn on the light, I start doing this, but then I discover there's a sub-goal, which means I need to get to the light switch. Or maybe there's like 10 boxes in the way to get to the light switch. I need to clean out those boxes first. So there's a lot of often like unfolding of these loops into hierarchies of sub-loops. Also, goals are often forgotten or discarded or changed, right? So meaning, for example, you may know this, goals are forgotten, often discarded or changed means, for example, you know how you, you know, you enter you go from your living room to your bedroom because you want to do something, and you get there, and you're like, what was it again I was trying to do, right? Yeah, we've all been there. I'm glad to hear that's not just a senior moment. And then what do you do to get back to that? You can go back to the other, isn't that amazing? You go back to the room, and you're like, oh yeah, right, I wanted to get the scissors to, you know, finish up, you know, packaging that parcel. You know, we forget goals, or we consciously discard them. We decide to do something else, or we change them, right? These things happen. And of course, also many actions are opportunistic and not planned that way. So, for example, you might run into, you know, your buddy on the in the hallway on the way to your next class, and because you see them, you're like, oh, we need to, you know, agree on a time when we want to work on that assignment that we're supposed to be doing, right? So that means you've now formulated a task, you know, find an appointment time, but that task was not something that, you know, just appeared out of thin air. It appeared because something concretely triggered it. Or, I don't know about you, but certainly not me, but some people apparently really get into high gear when deadlines approach. Not sure whether you've ever heard about this, but deadline-driven work among some people seems to be a thing. I'm sure you don't do this, but you know, so as a deadline is there, that, you know, gets you into doing certain activities too. So in general, you can say that the cycle can be goal-driven, as we, you know, modeled in the initial understanding of this 7 stages model, but it can also be event-driven, right, where it's coming from events that happen in the world. Now, that's the 7 stages model. Now let's look at what can go wrong. And the name that Norman chose for understanding or for labeling the problems that can happen is gulfs. A gulf meaning, like, you know, this abyss, right? This gap between 2 stages in this model is something that I need to cross somehow. I need to get across as a user to get from my goal to my plan, from my plan to my action sequence, etc. So this model of gulfs in these 7 stages of action helps us as designers understand where and why things could possibly break down. So it helps us both to design new interfaces, and it also helps us to rethink existing ones and improve them. When we see a gulf, when we see a usability mistake, we may be able to use the 7 stages of action model to say, oh, that's actually because there's a gulf between, you know, plan and execution of that plan. One example of what could go wrong is a gulf of execution. So something happening on the left-hand side of this, right? A gulf of execution would be something where I'm struggling with operating a device. Whereas a gulf of evaluation would be where I'm somehow having trouble determining whether what changed in the world is actually what I wanted to do, right? And of course, it could hit at each of these levels, right? And the role of the designer is to actually then bridge these gulfs, right? to actually address these problems. On the gulfs of execution, which are on the left-hand side, what can you do? Well, you can use signifiers, right? Label stuff to make it clearer what button people need to press, what kind of end of a package they need to tear to open it, etc. You can introduce constraints, which you also know now as interface designers, to keep people from going down the wrong path. You can use good mappings, natural mappings, to make it intuitive how to, if I say, oh, I want to turn on that light switch up there, maybe the light switch has a clear up and down direction. Up is light on and down is lights off. So I don't need to worry about which way I need to operate that light switch if I want to turn on the lights. And then finally, of course, you got conceptual models that you need to think through. If you build a good conceptual model and build it into a system image, user picks it up, and it replicates well, so to say, then you can also help people with these gulfs of execution. And in the evaluation, similar things are true, but also providing continuous and good feedback, and also, again, conceptual models is something that you can use to address the gulfs of evaluation. I know this all sounds a bit theoretical, so let's look at a couple examples. My favorite example here is, I think, the bag of peanuts. You've all been there, right? Even a simple action like opening a bag of peanuts can be surprisingly difficult. Why? Well, one reason is I can't even see, like I have a goal, it's like, me want peanuts, right? So very, very vague, right? I'm like in low blood sugar, and I want to open the bag of peanuts, like apparently, right? But I had no plan yet how to actually do that. So I pick up those peanuts, and I can't figure out how to open that bag of peanuts. There's nothing on there that looks like a tearing label or something that suggests to me how to best open that bag. If I then run into the issue that I do have a plan, but I don't know how to execute it, then I'm at the next step, right? So when I say, okay, I think I need to like tear off a corner up there to open it, right? But then it's unclear where to best grab this thing and where to pull and how to do that. So then I run into an issue there. Why is that a problem? This is often because I'm missing mappings and signifiers and so on that work well. And then finally, of course, my favorite when this happens is, how they sometimes put a little red plastic tab on these things, right? Where you like pull here to open this, right? So that's great. At this point, I've got my hazy goal. I can get from my goal to the plan. I know I want to pull this. This tab open, and I can actually break this down into an action sequence. I hold this in your left hand, reach out to the tab and pull it to the right, because that's obviously all given by the UI. And if it then actually opens, everything is great. If, I don't know about you, if it then pull on this thing and like it opens for like 6 millimeters and then it tears off, then the execution sequence failed, right? So I can actually even fail when I'm trying to do the execution of that action sequence, and then still no peanuts. So I also like to call this sort of the Amazon effect, because when you get Amazon parcels, more often than not you pull on one end and then it doesn't open, although they've gotten better lately. So that's a typical example of how the gulf of execution can basically stop me at different levels. So the gulf of execution opens up because we have differences between what the user plans as actions and the actions that the system offers, which, again, goes back to affordances, right? Because affordances are the things that we see in an object on how we can use it. Ideally, if your design really nails it, the system lets the user execute any actions that they plan directly and without any extra effort, because it's so clear how to use it. And yeah, sometimes I wonder whether I should show more really good user interfaces here to give you good examples. But bad user interfaces are so much more fun. So we're going to look at a bad user interface again. This is a Bluetooth headset. Yeah, like, ooh, warning label. One warning label that this Bluetooth headset is, it has a mode button, right? As I said, mode buttons are, I consider them warning labels. Norman doesn't talk about this much, but I think they are really a major problem. So let me tell you what this thing does. So it has two buttons which you can press to adjust the volume, and it has one button called mode. That's all you get on this one, right? Now, how do you operate this? Well, you need to press these these buttons. I think it's always the mode button that you press, but depending on which state your headset is in and how long you press that button, you can do the following. And I need to read this off because the list is amazing. You can use this to turn on the device, okay? You can use that to turn off the device. So when it's on, there's some way of pressing that button, maybe hold long press, I don't know, to turn it off. You can use that button to pair the device. You can use it to initiate voice dialing, so where you like say a number or a contact, and it tries to call that contact. You can use that button to do repeat dialing, and you can also use it to stop a dialing that is going on. And here's my two favorites. You can use that button to take a call or to reject a call. It's all on the mode button. And hanging up is also on the mode button. Now you might say, well, that's crazy, but no. These designers, they have you covered because some, not all, but some of these functions are actually really easy to tell what's going on because there are two blinking colorful LEDs on the headset, which you have in your ear. Okay, so you see where I'm going with this. So this device is breaking a bunch of rules that we've talked about, right? Visibility is horrible, right? I cannot really see the state. And even if I can clearly see that blinking red LED on it, assuming I've taken the headset out of my ear, I'm looking into a mirror, I don't know. Even if I see the LED blinking red, what does it mean, right? If I don't happen to have the user manual in my pocket or have learned it by heart, I have trouble interpreting that, right? So I have trouble perceiving what's going on because it's an LED blinking in my ear, and I have trouble interpreting the result too because the blinking LED doesn't mean anything, right? I don't know whether that means that the battery is low or whether it's trying to Bluetooth connect or whether a call is coming in. So visibility is a major issue in this one, but also mappings, of course, right? So we see that this thing, and any device that has way fewer buttons than functions should make you nervous. Right? And this is an extreme case, right? Because it has only a mode switch. So the mode switch is constantly changing its role, right? So you don't have a way of establishing a learned behavior of saying like, oh, this is how I operate this thing and how I Bluetooth pair it in the morning or something. None of this is something that you can easily appropriate as an action that you do because it's all only on one button. So you always need to check carefully, is it in the right state? Is the button going to do the right thing when I press it now? So it's a question of consistency too, right? Consistency drifts radically in this example because sometimes the button will hang up a call, sometimes it will initiate Bluetooth pairing, and it depends on what state the system happens to be in. So lots of problems here, both in the gulf of evaluation, but also in the gulf of execution here, of course, because it's really, if I gave you this headset, you would have no way to figure out how to even, you could come up with a plan or like a goal. I want to, place a call. I want to repeat dialing something, but you would have no way of turning that into an action sequence, right? Because this thing isn't telling you what the functions are that are available. They're not visible. The current state is kind of encrypted, if at all visible, and how to get to these functions is also not clear. So it's kind of like a tiny little black Swedish hairdryer in a way. Now let's look at the gulf of, oh, you had a comment? No. Okay. So gulf of evaluation, we'll look at this one next. Oftentimes, not just with this headset, but oftentimes it's unclear whether an action was actually successful or what its effect was. And the problem here is missing feedback. Norman talks about feedback quite a bit. It's an important part of the visibility concept. And in an ideal situation, you've got your system that gives you the system state clearly visible and also easy to interpret. And the way that it's done actually matches your conceptual model of the system, right? If that works out, great, we're covered. But I don't know about you. I have occasionally walked up to printers, and the printer, I'd send a print job there, and there's a green blinking LED. So you're like, is it still, transferring the data? Is it still getting the PDF sent over from my computer? Or is it out of paper? Or is it updating its firmware? I don't know. It's a blinking green LED, right? So here I can clearly see the LED blink in green, so perception is not a problem, but interpretation is a huge problem. Right? We don't know. Maybe it crashed and it's not even doing something. And does anybody remember the game Myst? Is this, yay, okay, thank you. So what was part of the, yeah, totally outed himself there. And so what is part of the fun in playing Myst and what's the game, what's going on in the game most of the time? Right, exactly. So it's a puzzle game. You can interact with stuff, but most of the time, like you would enter like a hut, and there's like a lever on the wall, and you're like, oh, it's a lever. I'll operate that lever, and then something on that island changes, right? Like on the other end of the island, maybe that opened a door or something or whatnot, but you don't really know. There are sometimes like little cutscenes that kind of hint at stuff happening, but before you know it, that's gone. And so part of the fun in Myst is figuring out mappings, right? Figuring out the cause and effect of your interactions with the environment, which is great for a game to occupy your time, right? Not so great for a user interface, right? So don't build Myst adventures when you design interfaces, because everyday things should not be that challenging. So we basically now have seen that we have a whole bunch of gulfs that we can run into, right? Where they can happen from goal to formulating your plan. If the thing doesn't tell you, if I can't even see, for example, with the headset, I can't even see if it does support voice dialing, right? I couldn't even come up with a plan to do voice dialing because it's not telling me that that's possible. So I can't even formulate the plan. Moving from the plan to specifying an action sequence, when I'm like, okay, my best friend told me this thing does voice dialing, so let's figure out how to do this. Again, you would be stuck, right? Because it doesn't give you any indications on how to do that. And then finally, if you know what your action sequence is and you try to perform it, you may still fail with certain interfaces. I like to think of that little torn off red tab on the package opening, ripping open a parcel and then failing to do that. That's the execution side. So on the other end, we have the evaluation side. So we may perceive things well, or we may not be able to perceive them well. Sometimes maybe that instead of the green blinking LED, maybe you have a very dark LCD display that only reads well when you've got the right light levels, etc. Or maybe you can't even maybe there's nothing on there at all. I think what was the device here that it really surprised me? I think the new HP printers will pretty much come with no interface at all. They don't even have a display built in anymore to speak of, because they expect you to fully use them with the app, right? So that's great when you have the app, but if you go into your friend's house and he's got one of those printers, you're like, huh? How are you going to print something? So that's an example where the interface isn't even there. But even if it's there and you can see it, like the famous blinking LED, then it's hard to interpret sometimes. And once you are able to interpret it, do you know what has happened now, and can you compare it in reasonable ways to what you wanted to achieve? Do you know whether that print is on its way out of the printer or whether you're not there yet? So for example, there's one thing that I should clear up, which is we found in past years that students sometimes confuse this. So if you have a goal and you end up not being able to complete it, that doesn't always mean that a gulf was at work, For example, if you send a document to the printer and it prints it, and you pick it up and you find that you printed the wrong document, that's not, the 7 stages worked, right? None of the gulfs triggered here, but apparently you made a mistake earlier on, and that's a different story. That's a story about user mistakes and user slips, which we'll talk about in one of the upcoming lectures, and I promise you the frozen pizza will be back then as well. So in all, what we can say is that the 7 stages of action, actually, when we take it as interaction designers, can serve as sort of a design guideline, right? So the questions here are really good questions that you should ask yourself as you design an interface, as you look at a prototype of a UI, to figure out whether you can find good answers to them. So first thing is, what do I or what does the user want to accomplish? This is the question of the user's goal, right? What is their initial goal? And then the next question then is, what would be alternative plans to achieve that goal? What would be alternative action sequences to formulate to get to a plan? And then the next question is, all right, now looking at this concrete device and my plan of achieving my goal in some way, what are the concrete actions that this thing supports? Think of the Swedish hairdryer, right? If I wanted to heat something up really, really strongly, I may want to understand, oh, can I crank the heat up on this thing any further, or am I already at the maximum setting, right? And then if I know, okay, this thing has another heat level, then I need to know how do I get there, right? So that would be, how do I do what I'm intending to do? And then next, I want to understand, did I get there? Did I actually reach, heating level 2 on that hairdryer or not? And being able to physically perceive it, if the 2 labels on the hairdryer are green and yellow, then I can see that I moved from green to yellow, but does that mean that I actually cranked up the heat? Unsure, right? So I need to be able to interpret and understand what it means, what I'm seeing, to see whether I actually then finally can answer the question of, is this okay? Have I accomplished my goal, and can I do a reasonable comparison to that? And each of these stages in the end requires its own sort of design strategies, but the 7 stages model is a good way to think through what is going on and how to get to through the various stages in order to actually arrive at a reasonable result. Okay, we're going to summarize things here for today. What we saw were, first of all, mappings, right? We've talked about spatial, perceptual, biological, and also cultural analogies that create good natural mappings, right? We've also talked about constraints, right? Constraints being sort of the flip side of the coin, if you want, of affordances, right? Constraints keep you from doing certain things, whereas affordances guide you towards doing certain things. And we distinguish physical, semantic, logical, and cultural constraints here in this context. And then finally, we've seen the 7 stages of action, which is, I need to say, just like Fitts' law or like CMN, right? All these models are engineering models of how humans work, right? We don't really have these 7 stages, that we clearly can distinguish in our brain, but it's a good enough model to look at a problem, to tease it apart, and figure out how to make a good interface. So they're engineering models. We especially use the 7 stages of action model to identify gulfs, both on the execution side and the evaluation side. And when you go through it, you get from goal planning, from the goal to a plan, to specifying an action sequence, to performing it, to then perceive the results, interpret them, and compare them to where you want it to go. All right. Finally, what I'd like you to leave with here for today is we would like to ask you to continue reading Norman's book, right? We are now roughly at page 120 or 122, I think, is the end of what you should be reading in order to familiarize yourself with the material that we've covered here. With that, we can wrap up a little earlier today, so you may have a chance at getting a prime spot at the lunch Mensa queue. Thanks everybody for listening. Goodbye.
This content was provided by RWTH Aachen University.